This video helps you to learn how to find Hamiltonian cycle for a graph using backtracking technique. So what is Hamiltonian cycle? Let's take a graph of n vertices which is represented by G. G is having set of vertices V and set of edges E. We are going to represent this Hamiltonian cycle by an output vector x, which is a set of values of x1 to xn, which represents the order of visiting vertices. That means in the Hamiltonian cycle means it's a round trip along n edges of G that visits every vertex once and returns to its starting position. For example, if it starts from the vertex V1, the vertices of G are every vertices of the G are visited in the order V1, V2 up to Vn plus 1. Then there are two constraints we have to check there. One is there should be an edge from V1 to V2. Similarly, V2 to V3. That means for every vertex Vi, there should be an edge to Vi plus 1. And the vertices V2 to Vn should be distinct. That means the starting vertex V1 and the end vertex Vn plus 1 should also be V1. Right? Only this V1 should be occurring twice. All the remaining vertices should be distinct one. That means it has to start from one vertex, visits all vertices and returns back to V1. So let's see an example. So in this graph, we are having 8 vertices. 1, 2, 3, 4, 5, 6, 7, 8. Let a person starts from 1, visits vertex 2, 8, 7, 6, 5, 4, 3 and 1. So he is starting from this position 1 and returning back to this position 1. As he is has visited all these vertices, this cycle is known as Hamiltonian cycle. But let's take one more example. If it is starting from 1, 2, then 8, then 7 and then back to 1 means this is also creating a cycle, but this is not in this cycle. We haven't visited all the vertices of a cycle of a graph. So this is not a Hamiltonian cycle. Okay. So let's see how to find this Hamiltonian cycle using backtracking technique. So for this, let's illustrate the example first. Then we will explain the algorithm. For this graph, let's create a adjacency matrix. So adjacency matrix is a set of a matrix with n number of rows and n number of columns, and each cell value will be having value will be either 1 if there is an edge from one vertices to another vertices, and 0 means there is no edge between these two vertices. So this is a adjacency graph for this graph. Now we are going to represent the Hamiltonian cycle in this output vector. Initially, we are taking the first vector as 1. That means we are going to start from the vertex 1. Now, we have to see the order of visiting vertices from 2 to xn, right? And then we are going to see the last vertex as once again 1. Okay, so the last vertex will be once again 1. So, we have to check for whenever you are filling this vertex, we have to check is there an edge from this previous vertex to this vertex. So initially all these values are assigned as 0. From 2 to n, all the vertices are assigned as 0. Let's start with Hamiltonian of 2. Right? We are calling recursive algorithm. Now we are going to find which vertex should be visited after 1. So initially it is 0. Now we are incrementing it by 1. Now we are assigning the next vertex to be visited is 1. Already it is invested on it is in vertex 1. So it is meaningless visiting the same vertex again, and there is no edge in here. 1 to 1 is also 0. So increment it 1, right, by 1. Now it is 2. Is there an edge from 1 to 2? Yes, there is an edge from 1 to 2. So we can assign this as 2. And also we have to check that is this vertex 2 is already visited, as there is only one vertex which is visited before this and this is not repeated. So the vertex assigned to this position is 2. Similarly, we are going to see Hamiltonian of 3. So in this Hamiltonian of 3, we are starting with 1. 1 is already visited, 2 is already visited, so 3. So now we have to check, is there any edge from 1 to 3? Yes, there is an edge from 1 to 3. So we can assign the vertex as with 3 for the third position, and this vertex 3 is not visited before these two, before this, right? Now a Hamiltonian of 4. Now 1, assign it as 1, already visited, 2, 3 is also already visited, so fourth one, right? And for Hamiltonian of 5, the same case, 1, 2, 3, 4, 5. So we have to check, is there any vertex from 4 to 5? Yes, it is there. So we can assign it as 5. Now Hamiltonian of 6. So Hamiltonian of 6, the same case, 1, 2, 3, 4, 5 will be failed, and we have to check, is there any edge from 5 to 6? Yes, it is there. So assign it as 6. Now 7, Hamiltonian of 7. So Hamiltonian of 7 means, is there an edge from 6 to 7? Yes, there is an edge from 6 to 7. So 7 is assigned. Now Hamiltonian of 8. Is there an edge from 7 to 8? Yes, it is there. So it is assigned. As all the previous 1 to 7 will be failed, now the 8th position is 8. Now we have to check whether there is an edge from vertex 8 to 1. Here it fails, right? So we cannot take this as the final output solution for this Hamiltonian cycle. So we are going to see the state space tree for this. We are starting from vertex 1, vertex 2, then 3, and 1 in this position 1, 2 failed, so 3. Now 3 to 4, 1, 2, 3 failed, 4, and 4 from 4, 1, 2, 3, 4 failed, 5. Here 1, 2, 3, 5, 6, 1, 7, 8. As we cannot visit 1 again, so this becomes a dead end. So backtrack. See what are the other possibilities to visit the vertices from 7. There is only one possibility, either 8 or 1. So this cannot be completed. Right? Now let's see next question. So this 7 will be once again backtrack. Let's start from 6th position. What are the other possibilities to visit from 6, vertex 6? So from 6, what are the other possibilities? From 6, 3 is already visited, and 5 is already visited, and 7 is the next one. So 6 to 7 fails, right? So we are coming back, backtracking. So 5. From 5, we have to check whether there is any possibility to go to 7 as 6 is backtracked, right? So 5 to 7, is there any possibility? No. 5 to 8 is also impossible. So once again backtrack to 4. From 4, we have to check, is there any vertex for 6, 7, edge from 4 to 6? No. 7, 8, no. So backtrack 3. Now from 3, we have to check, is there any edge from 3 to 5 or 6 or 7 or 8? So 5 failed, and then there is an edge from 3 to 6. So let's take this tree, this branch. 3 to 6 is possible. Now from 6, we have to check what are the other metrics, what are the other vertexes we can visit. So already 1, 2, 3 is visited. Now 6 to 1 is not possible. 6 to 2 is not possible. 6 to 3 is not possible. 6 to 4. Is there any possibility to visit 6 to 4? No. So 6 to 5. Right. Let's check. If we are making 6 to 5, once again from 5 we have to check 5 to 7. So 7 to 8, 7, then again it will be failed. So this will be a dead end. Right. Now 5 to 6. So for 6 we have to backtrack again. Now there are two possibilities, either to 7 or to 8, right? Only two. So let's take 6 to 7. So 6 to 7 and 7 to 8. So that is also becomes failed, right? So backtrack, come to this position. From 2, we have to check what are the other possible ways. From 2 to 3. Already failed, right? 2 to 4, there is no edge. 5, no edge. 6, no edge. 7, no edge. 8. So 2 to 8. We are going to visit vertex 8. So from this vertex 8, we have to check. Is there any possibility to visit 1? 1 is already visited. 2 already visited. So we cannot visit this. 3. Let's 3. From 8, is there any vertex to 3? No. 8 to 4? No. 8 to 5? No. 8 to 6? No. 8 to 7 is there. So 8 to 7. Right? So now from 7. 7 to 1, 1 is already visited. 2 already visited. Right? 1, 2 is already visited. And 3. Let's 3. 3. Is there any vertex, any edge from 7 to 3? No. 7 to 4 is also no. 7 to 5 is also no. So 3, 4, 5, all these will be failed. Now we have to check 7 to 6. So 7 to 6 is there. So from this 6, once again we have to check. 1 will be failed, 2 failed because it's already visited. Now 6 to 3. Is there any way to, any edges from 6 to 3? Yes, 6 to 3 is there. So let's take 6 to 3. Right? Once again it will go from 3. We have to check what are the other possibilities. 1, 2 already visited. 4 is there, no? So let's take 3 to 4. Right? And then 3 to 4 is done. From 4 we have to check only 5. From 5 only 6. Again it will be failed. It will come to a dead end at some point of time. So let's backtrack once again. From 7, what are the other possibilities? So likewise you have to continue this until you get the succeeded value, right? So the final solution is from 1 it will go to 2. So from 1 it will go to 2, 2 to 8, 8 to 7, 7 to 6, 6 to 5. So 3, 4 failed. So 4 is, there is no vertex to 4, edge to 4. So 6 to 5. So from this 5, there is an edge from 5 to 4 is there, no? So 5 to 4 will be there. And from this 4, there is an edge to 3. So 3 will be coming. And from this 3, there is a possibility to go to 1. So the final answer is x1 is 1, x2 is 2, right? Refer this graph. x1 is 1, x2 is 2, and x3 is 8. x2 is 2, x3 is 8, and x4 is 7, and x5 is 6, 7, 6, and then 5, 4, 3, 1, right? So all these elements are distinct, and this one is same. It started from 1 and it ends at 1. So x6, x7, x8, x9, right? So this is the Hamiltonian cycle for this graph. So this graph is having the Hamiltonian cycle. So the algorithm is given here. Let's start with this algorithm. First we are having the input in a matrix G, right? And then we have to check the next value for K. For this next value of K, we have to check here. We have to assign value from 1 to, every time we have to increment value 1. X of K is equal to X of K plus 1 mod N plus 1. 1, 2 like that you have to increment it. And we have to check, is there an edge from the previous vertex to this vertex. If it is not equal to 0, there is an edge. So we have to check if there is an edge from the previous vertex to this vertex. Once again we have to check this vertex is not visited before. So if it is, we have to check from 1 to k minus 1. if any one of these vertices is not same, so this is a distinct vertex, and also we have to check if this is the last position. That means there is no previous, this vertex is not visited before, and now we have to check if this vertex will lead to the starting position, right? The starting vertex is reached means then we can return true. Otherwise, it will return false. We have to assign the next value for x of k. Repeatedly, you have to do it until you get this x of k is equal to n, right? So, this condition will be true if k is less than n. If k reaches n, it will return false. So, once it returns false means it will come here. Now, it will check here. If x of k is equal to 0, then it will return true. Otherwise, if k is equal to n, we have assigned value for all the vertices, all the positions of the vector, output vector, so we can display the value. Otherwise, you have to call Hamiltonian for k plus 1th position. So, this will be repeated and it will return false if there is no Hamiltonian cycle. So, what is the complexity of this algorithm? So, if you take this cycle, in the state space tree, from this vertex there are n minus 1 branches. From each of this again there are n minus 1 branches. So every time it starts from 1, n minus 1 and then n minus 1 whole square like this up to n minus 1 to the power n. So it is in exponentiation form, right? So the total complexity for this algorithm is n minus 1. It is in n minus 1 to the power n minus 1 divided by n minus 2. This is the complexity of this algorithm. Okay.